Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, construct the lexicographically largest valid sequence. So the idea is we're just given a very simple parameter n equals 3 in this case. And what we want to do is, first of all, this means that these are the numbers available to us, 1, 2, and 3, from 1 up until n. Now, the quantity of each element is a little bit different. 1 is going to have a quantity of 1. The rest are going to have a quantity of exactly 2. So a count of exactly 2. So I just want to make that very clear. Now, if we had like a 4 over here, there would also be exactly 2 occurrences of it. We're going to be focusing on this though. And so what we want to do is take like the aggregate of all of these counts. I guess let me kind of cross this out. So sum all of these up, we will have 5 slots in the output. We want to create an array with 5 different values. You can probably guess that we're going to have exactly 1 occurrence of this element. We'll have 2 of these and 2 of these. We first of all populate the array. We have like something that maybe looks like this, but this array has a problem. It doesn't actually satisfy the main constraint. What we want is for both occurrences of 2's to be separated by 2 positions. So meaning the distance between them, like this is at index 1, and the next one should be 2 positions away. So either on this side or maybe on the other side. But right now it's clearly not. So we could do some rearranging. We could have actually created an array that looks like this, 2, and then I put the 3, and then I put the 2, because I kind of have to, it has to be separated by 2, and then I put the 1, and then I put the 3. Now, there's one small problem with this approach. While it does satisfy the constraint, what we want to do is actually create the largest valid sequence. So basically, like if you were to consider like this entire thing as like an integer, we want to create it, the largest one. And we can do that in this case very simply. If you just take this and reverse it, you'll get the other number that looks like this, 3, 1, 2, 3, 2. So this also satisfies the constraint because you can see that 2 is separated by 2 in this array, 3 is separated by 3. Same thing for the array at the bottom because it's literally just a reversal of this one. But this one is larger than the other one because this one starts with a 3, this one starts with a 2. So to create the largest number, my intuition told me maybe there's a greedy solution to this problem. I think it's pretty trivial to recognize that there is a brute force solution to this problem. Like the brute force solution would be just like enumerating every single permutation in the input, trying every single one until you find the best one. And even that's going to kind of have like a greedy component to it. So like that solution to me was pretty easy to recognize. Like that falls under the backtracking pattern, which is pretty extensively covered on Leetcode.io, whether you use like the free resources or the paid ones. So if you're not familiar with this, definitely would recommend solving some easier problems before tackling this one. Definitely learn some of the basics first. To get back to this problem, in terms of like what I would do in a real interview, I would definitely mention like the brute force solution. And the reason I'm telling you that is when you kind of have some problems, it's really hard to tell if you can actually do a better one. I think that's like one of the most annoying things about backtracking to me. Sometimes you don't know, like, is the backtracking solution, the brute force one, the most optimal? Or maybe there's like an actual better approach. There's some kind of trick to this where we can intelligently rearrange the numbers where we can solve it more optimally. Maybe that would be like an n squared solution, or something like that, but it wouldn't be exponential. It wouldn't be like n factorial, which is growing insanely quickly. Just in case you've forgotten like some of the time complexity stuff, remember that if you have some constant to some power n, that's always going to be like slower to grow than n factorial, which is going to be slower to grow than n to the power of n. This is just some math here. You don't really have to probably deeply understand this, but I would probably recommend understanding it like on some kind of intuitive level. But anyways, in this problem, the main way you'd be able to recognize this is a backtracking problem is the constraints in this problem. The constraints specifically say that n is going to be bounded by 20. So even if you were to take like 20 factorial, it's going to be a really large number, but it's still going to be reasonable. I think it's probably going to be in the billions or something like that. With like modern CPUs, I don't think that's like going to be insane. But if you were to grow this number, like maybe set it to 100, then that would be very much slower. It would not be 5 times slower. It would be a lot slower. Because remember, this is growing proportional to n factorial. And actually, I just checked on my calculator, and 20 factorial is actually much larger than a billion. It's like 2.4 times 10 to the power of 18. But even then, I think that's not like the end of the world. But if you raise this to like the power of 5, and then all of a sudden this becomes like a 90, and this becomes even bigger than it is, well, now our algorithm is very slow. Not 5 times slower, but a lot slower. Now, in a real interview, like what I would do is definitely try to spend at least a little bit of time trying to think of like a better solution, but I would be thinking out loud. Like I would tell the interviewer, okay, so I've recognized that there's probably like a brute force solution to this. It involves backtracking. It might be a pain to code up, but it's definitely doable. But I wonder if there's a better solution. Maybe your interviewer will let you kind of explore that there might be a better solution. Maybe they'll just nudge you to code up the brute force solution first, and then you can try coming up with a better one. I don't know, but it's always worth being a little bit explicit about what you're doing like in the moment. Okay, so with all that said, let's get into the backtracking solution then. So in this example, remember we have 5 slots. Now, how exactly do you calculate how many slots you have? Given that n is 3, how do we know that we have 5 slots here? Well, it's not super crazy. We know that for each of the elements, there's going to be exactly 2 of them, except for the first one. So we could say, well, we have n elements, 3 of them, 2 times n minus 1. We get the minus 1 from this. There's only 1 of them, not 2 of them. So I'll just move that down there so we have some space here. Now, how should we go about doing this? I mean, one way to reason about this would be to literally try every single one, and then among all of those, you compare them, and then by doing like some kind of comparison, we can determine which one is the largest one. That's fine. I mean, it might work, but there's definitely a better approach, and it's probably actually easier to code up than this one, which is to be a little bit greedy. I mean, it's still like a brute force solution, but we're doing it in a greedy way. What exactly do I mean? Well, first, let me show you my handy dandy decision tree. So we know that for the first spot, we have some choices. Now, what are the choices? Like how you break this down, there's some difficulty involved in this as well. I'll try to address it. But mainly, we have at least 3 choices. We have the 1, we have the 2, and we have the 3. Now, if I were to place the 1 here, that's fine. And I would probably just place the 1. I mean, there's just a single of them. So I can go ahead and place it. Great. If I was going to try the 2, that also works. But as I'm placing this 2, I might as well place the next 2 because I know that it has to go in this position. I'm going to work by filling this in left to right just because it's the most straightforward thing to do. So it makes sense for me if I'm placing a 2, I should place the next one right there. It has to go there because we've already filled in everything that came before. And obviously, I could have made the other decision as well. I could have placed the 3, and then I would have made sure that the next 3 had a distance of 3 from the other one. So those are my choices. Now, when I say I'm going to be greedy when I code this up, I mean that I'm going to choose which one of these I place first intelligently. We want to create the largest number. So if I'm being greedy, I should try the first number to be the largest one. I should put the biggest number over here. And by doing that, I guarantee that the first solution, the first valid string or array that we're able to create is going to be the largest one. So that's what I mean when I say we're going to do this greedy. It may not necessarily be possible that the most greedy solution will actually be like a valid solution. We might run into some invalid arrays, and then we will have to backtrack with our decision tree. So now with most of that intuition out of the way, let me just kind of do the dry run. So this is how it's going to work. Instead of making our decisions like this, I'm going to have my first decision be the biggest element. So I have these elements, and in terms of coding this, many ways to do it. I'm just going to iterate over the elements that we have in reverse order, and I'm going to see how many are available to us. And actually, I'm not even going to keep track of how many. I can actually just use a hash set. I'm going to call it used. And what it's going to do is it's going to keep track of which elements have already been used. So as we iterate through this in reverse order, we see a 3, it might already be in the hash map. That's how we will know that we can skip it. The reason I can have like a true or false to determine if a value is available or not, and I don't need to keep track of the count, is because when I place the 3, I'm going to place both of them at the same time anyway. So it doesn't really matter what the count is. The main thing, though, that we will have to differentiate between is if our number that we're placing is equal to 1, well, it's only going to go in one position. But if the number that we're placing is something like 3, we have to make sure that the current position that we're at, let's call that index I, is available. And we also have to make sure that the next element, wherever we're placing it, that position is also available. If that's not the case, then we can't place the element. And then we will continue to iterate. We will then have to skip this element and maybe try the other one. It'll probably make more sense as I do the dry run now, but I thought these things were still worth mentioning. Okay, so what I'm going to do here is I'm going to try the 3. So what do? I check, is this spot available? It is. And then I check the next spot over here. It's free. And we can kind of initialize the array originally with all zeros to check that those spots are indeed free. But now we've done that. So now we're going to go to the next available position, which is this one. And from here, we're going to try another decision. We want to be greedy. So, I mean, we can try the biggest element. It's 3. It's not available to us. We will have added that to our hash set. So now we'll try the next one. It's 2. So let's make that decision. Let's try 2. So I'm going to put a 2 over here. And then exactly 2 spots away, I'm going to put the 2 over here. Oh no, we have 2 elements in the same spot. So we actually can't place the 2 over here, because if we did, we wouldn't have enough space for the other 2, which has to go here. There's no other choice. We filled all the elements that came before, and we did that to make our life easy so that we wouldn't have to worry about 2 different directions. But now we kind of screwed up. So what do? Well, that's the whole point. You backtrack with backtracking algorithms. You undo what we did. So the 2 did not work. I'm going to try the other thing, which is 1, the next available element. And so I put 1 here. And with 1, we know that it's a special case where we don't have to place another element. So that's good. So let's keep going down this path so far. This one would have been larger, but this one was invalid. So we cannot continue down that path. So now the only element that's actually available to us is 2. So we make that decision. We try 2 and we put 2 here, and we see 2 spots down, 2 over there. And so at this point, we are done. And the good thing about this problem is there's guaranteed to be a valid solution to the problem. So the first valid one that we see with this greedy approach is going to be the one that we return. One minor thing I think that's worth mentioning, when we are at a position, like we have our I pointer, it starts at 0 at the first position. That's what we're trying to fill. To go to the next position, it's not as simple as just saying I plus 1, because for all we know, this position might not be free. How do I know that? Because look at this. When we added 3, we added another 3 over here. Imagine that this array is longer. It keeps extending in that direction. Well, eventually, as we fill that in, our pointer is going to end up over here, and this element has already been filled in. So we would want to skip that. So the way I'm going to handle this is just by having a loop. So when you see my code and you wonder why I don't have an if statement and I'm using a loop, or why I'm not just incrementing it by 1, now you kind of understand. Okay, so the way I'm going to set this up is pretty important. So I'm going to have my array. I'm going to initialize it to be of size 2 times n minus 1, and it's going to be all zeros initially. And then I'm going to have my used hash set. This is going to keep track of the numbers that are already placed. And what we're going to do is return the result, and we're going to have most of our code go inside of this function. I'm going to call it backtrack. It's going to take a single parameter telling us which index of the result we are currently trying to populate. And so this function, after we call it, we can expect that it will fill in the result variable that we declared outside. So we will start the backtracking from 0 and then go left to right. Okay, now in terms of the base case, since we are going from left to right, it's pretty easy to recognize that once we get out of bounds, that's when we return. And we assume that if we've reached out of bounds, every previous decision that we've made here, wherever we do like the recursion, We assume all of those decisions were valid. We will validate those decisions before we make them. So we can assume that if we got this far, we can go ahead and return true. Okay, so now for like the code down here. I'll try to leave some comments to make it clear what I'm trying to do. I'm trying the largest elements. So I'm going for num in range from 1 to n plus 1. The n plus 1 is not inclusive in Python, so this means I'm doing 1 through n. But I want to go through those in reverse order. In Python, it's pretty easy. Just do this. So that's what we're doing. A couple things we need to check before we can actually do the recursive step. This is the part where we're doing the validation. So I guess I'll make a comment. One is if this number has been used. If this is in the used hash set, well, definitely continue to the next iteration of the loop. Try the next element. And the other one, which I could include here, but I'll write it down here just to make it a bit more readable, is the case where the number is greater than 1, meaning that we're going to have 2 copies of that element to place. And then we have to make sure that this is true. If the result at I plus num is already occupied, we can assume that the current index is not occupied because I'm going to have like some additional code down here to do that. So that's why we're just checking I plus num. If this is not 0, then we would also want to continue. Now, the reason I put this in parentheses is we might get an index out of bounds error here. So before I check that, I have to check that I plus num is still in bounds. But I should probably do the opposite, though. I should check that if it's greater than or equal to the length of the result, or this is true. If either of these is true, well, then we have to skip the current element, because either we will go out of bounds or that position is already taken. Okay, so now we've done the validation. So now we move to the recursion. So before we can make the recursive call, we're going to do a little bit of pre-work, which I guess I'll say we're trying like this decision. We're going to take the current number, add it to the used hash set. Most of the stuff I'm going to be doing right now is pretty simple. We're also have to differentiate between like if number is equal to 1 or otherwise, because for 1, we're just going to place it at result of index I. But for numbers greater than 1, we're going to place them at result index I and result index I plus that number. So we'll have code that looks something like this. If you're clever, you see there's a little bit of repeated work here. We have this line here and this line there. Why not get rid of this case, change this to if num greater than 1, get rid of this code because it's already up above, then I'm done. Okay, and one last thing before we can do the recursive step is the index. So the next index, which I'm going to put in J, we would expect it to be I plus 1, but it's actually possible that that spot could be taken. So we will do this while the spot there is non-zero. So it's greater than 0, or you could just do this in Python. While it's non-zero, then continue, then increment J. But we also have to make sure we don't get out of bounds. So let's also check that J is less than the length of the result. Okay. After all of that, we're ready to do the recursive step. So now I'm going to call backtrack. Remember, this function is returning whether we were able to find a valid sequence. If we do, then we can immediately return. The first one that we find is the one that we care about. So if this returns true, backtrack from J, well then just go ahead and return true. Otherwise, maybe it doesn't return true. And yes, it's true that at some point we would want to return false. But we haven't necessarily exhausted all of the decisions. Maybe there's still some elements for us to go through. So if that's the case, we want to backtrack before we try a different decision. This is basically how backtracking works. Like this is the template for backtracking. You try a decision. You do the recursive step, like you do the pre-work and then you do the recursive step. And then if you don't end up like finding the solution, then you backtrack. You undo the step that you took before the recursive step, which is all of this code here, mostly this part. So I'm just going to copy and paste this code because we're just going to kind of modify it around. So this we can remove, I think, with the remove function. And this, we can undo that just by setting this to 0. And same thing here. We can undo that by just setting that to 0. See how easy that was? Maybe it's not easy for you. It's probably because you're new to this stuff, or you just haven't practiced as much as I have. But for me, it's pretty easy because I've done this so many times. It's like a template that I follow inside of my head. So unfortunately, the code is kind of small if I want to like display it all like on the same screen, but I tried to keep it like mostly readable. Let's give it a run. And here on the left, you can see it is pretty efficient in terms of time and space. If you found this stuff helpful, check out Leetcode.io. If you struggled with this stuff, I would especially check out Leetcode.io. I hope there's some resources on there that can help you, even if you just stick to like the free stuff.